if it satisfies the following inequality, so to say, if for some constant c for all x, and f of x is smaller than maximum c and x to mean that the maximum of all the input values, so to say, of that function. Okay, so these functions are, of course, essentially the functions which eventually are below, so to say, the identity function. So they don't grow. And successor function notably does not satisfy this condition because x plus 1 is always bigger than x. And okay, so but the first point was well, that one can, instead of dealing, let's say, with plus times and successor, we can deal with instead with predecessor, minus, and division, for example. And essentially, in terms of expressibility, if we allow quantifiers, we don't lose anything, right? So we could have even had relations instead of functions. But another requirement which, so the first step what we do, we will enrich. So what I would like to say is formulate the following thing. There is an extension of the language of PA, of relational PA, let's say, by a set of non-growth, let's say primitive recursive non-growth functions. So the set of these functions will be denoted L, satisfying certain properties. And okay, so the first property is that what we want to have is that all syntactical, all the usual syntactical notions are, we know that they will be definable in L already because they are definable in piano. But we want that they are definable by a special kind of formulas, namely the formulas which are bounded. Bounded in the sense of the new language. So are definable by what I call delta 0 of L formulas. That is, once again, the formulas which may contain symbols from L, so to say, the usual first order formulas, I would say, but equality, but all the quantifiers occurring in these formulas must be bounded, that is, have the form of x smaller than t, something for the
Lev, I have somehow lost the thread.
Here.
Do you define now conditions of some theorem or what?
We are defining conditions which we want to satisfy. Then I will say there is a theory satisfying these conditions, and then we will build from that theory another theory.
Okay, these are conditions on some arithmetical type theory. Okay.
Arithmetical type theory.
Yeah, but also I have another question. Imagine that this L's are non-growth functions.
Are non-growth.
But they are primitive recursively, and so they are expressed in terms of other and so on. But do we require these others also are non-growth, or we are allowed to use anything?
So far what I said was just that every individual function from here is non-growth, and it is actually primitive recursive. We don't care how it is built, but more honest answer would be yes, we will require that they are also built from non-growth functions, and that will be the way to build such a thing. But it can be built in various ways, and what I will be presenting will be kind of what I think is simplification of what Willard does. He does it in a more complicated way, and I will build more in the spirit of primitive recursive functions. But okay, so that's one condition. And by usual syntactical notions, what I mean, the notion of being a variable, being a term, coding of sequences of symbols, the notion of being nth bit of of a string of zeros and ones, things like that. So all this usual stuff, which is usually defined in primitive recursive functions, let's say, will be defined here using only these restricted non-growth functions. Of course, the most important thing here will be two, namely the proof, predicate, and if you remember the last lecture, so this proof predicate is built in some canonical way, so to say, having enumeration, a formula defining axioms for the theory. So I require that term will be, so to say, delta 0 of L alpha, to mean that alpha is a sort of second order variable which may be occurred inside this bounded formula. So when we substitute for it some delta 0 of L definition of a theory, we will obtain an honest delta 0 of L proof predicate. Right? Okay. So if alpha is delta 0 of L, then F alpha is. Okay, and there's another function which also is important, as we know, for variables in completeness, and a substitution function, right? Which means something like sub x y, which means that we substitute in the formula with Gödel number x the term representing the numeral y for the first variable. But, okay, substitute Gödel substitute.
But it's a function or predicate?
It's a function, but we want it to be a predicate that this is a delta 0. That's true. So, Gödel substitution. So usually all these things are done with primitive recursive functions, but so the task is to do it only with non-growth functions. Okay, so this is the first requirement. Now what was the second requirement? Okay, and now this is about defining things, and now we say that there's the rest of the requirements are requirements about the theory T0, which is in this language. And the theory T0 is axiomatized by pi 1 of L formulas. By pi 1 of L, I mean formulas of the form for all x delta 0 of so formulas, delta 0 of L formulas prefixed by a number of unbounded universal quantities. So analog of usual pi 1. Okay. So we require that every axiom of the theory T0 is like that. And in the context when our functions are non-growth, what I want to say is that this is of course a very severe restriction. So we have no chance, well, let's say, to achieve something equivalent to piano arithmetic having that restriction, because when we convert, so to say, usual functions plus and times in terms of relations, for example, we introduce unbounded quantifiers, or at least quantifiers which are not bounded by non-growth functions, of course. So this would not be possible to do it here. So T0 is in that sense much weaker than PA. And in fact,
but now if you don't if you just allow any non-growth function, somehow you probably can just add some variable which encodes something, and then you take all the function of this variable which are smaller than it, and
that is more or less the idea how we achieve item 1 here, right? So this, if I understand what you are driving. So in some sense the expressive power of the T0 is very small because it cannot produce any real growth, but it can do a lot below any fixed constant, so to say, or below the given variable, so to say. So it can define functions like logarithm, for example, and so on and so on. So that will be...
No, but logarithms are just in L.
Of course. Well, we don't know what is in L, but of course it will be in L, yes.
Oh, yeah.
But anyway,
Yeah, here we'll miss.
later we will see some more details, but some questions will be seen here. So that's just first condition that we want. But the point is that this condition even prevents T0 from having successor as a total function. Because of another lemma I will explicitly formulate later, but the theory will have finite models. Okay, so T0 is axiomatized in this way, but the set of axioms of T0 should of course is delta 0 definable as it should be. But it is also, I would say, in P. Also in P. If you question whether functions there are too complex or something, but of course it will be quite constructively given. So that's the third requirement. Okay, and there will be a couple of more requirements which are sort of given in addition to that. So T0 is able, T0 proves fixed point lemma.
Also called reflection principle.
No.
No?
Fixed point lemma is the following. So fixed point lemma. It says the following. So given a formula phi of x with one free variable x, one can find a sentence psi such that, in our case, T0 proves that psi says of itself that it satisfies phi, property phi. So psi is equivalent to phi of the Gödel number of psi.
But why it's different from reflection principle?
No, reflection principle is something is provable, then it's true.
Yes.
Why it's not just a
Okay,
name.
okay. Forget
It's just a matter of terminology. But
Yeah.
you probably
Okay.
meant this, but you thought that.
Yeah.
But reflection principle is, well, as Sasha said, something.
It's also not the second law
Okay,
of
it's not,
thermodynamics.
I'm
yeah.
sorry, it's not my fault. Somebody else told me that this is.
That is possible, but listen to what Sasha says.
Okay.
So, one point of a comment here, what is this Gödel number of psi in terms of this? So this is of course a closed term representing the natural number, but our terms are non-gross. So if we have, for example, one constant 0 in our language, we cannot produce any denotations for numbers bigger than 0. So the solution is that in our language we will simply have constants for all natural numbers, and that's it. So we have, our language has explicit constants, 0, 1, 2, 3. So our theory is not finitely axiomatized.
But there should be also some axioms about it.
There will be some axioms about that. So I have not formulated all conditions,
Okay.
or rather, I have formulated, for example, rather complex condition number 4, which would not be, which would not hold if we didn't have any properties of this one.
But what you say is not just a formal conditions, it's just kind of promises for the future.
You can say that this is promised for the future, but I think that they can also be considered as formal conditions. I mean, but they are not very nice. I mean, conditions something like 1, 2, and 3 is fine, but condition number 4 is a kind of non-elementary condition. So I would.
Also, I would not say that the condition, all the usual things are definable. It's very formal, but still okay.
Yeah, okay. You're right. But I could have just restricted myself to these two, so to say. But again, to come to these two, one has to formalize everything which they are built from. So it's a promise that we should do all the work Gödel did for primitive recursive functions here, basically. And this was the major technical part here. So if you think about it, And of course I will not be able to present it in full, but I will at least indicate some ideas how to do it. So we have fixed point lemma, which is a crucial thing for that. And concerning with fixed point lemma, we know that it holds in PA, but it was well known for a long time, so already since Pfefferman, that fixed point lemma actually holds in Q, in this very big Robinson's arithmetic cube. What is the reason for that? The reason is that the only thing which is needed for formulation of that formula psi is basically a definition of this substitution function. So our theory must represent the substitution function in the sense I described. So for every fixed numerals x and y. So if we substitute constants for x and y, our theory will be able to prove that there exists only one value of that function, and that's so the value is unique. So that's okay. Let's leave it at this at that level for now, and let us now formulate what we want to do. Okay, and maybe the fifth condition is that in fact our T0 contains nothing false, so to say. T0 is a true theory. So T0 is true in the standard model. In fact, it is a sub-theory of piano arithmetic. Piano arithmetic can be interpreted. It can be interpreted, and in fact, T0 can be is contained in things which are much smaller than piano arithmetic, like I delta 0 plus x, but we don't need to know even what is this to have this. Okay. Okay, so then the theorem sounds like this. So if we have constructed this theory T0, then there is a finite extension, finitely axiomatized extension, so to say. We add to T0 a single axiom such that that theory actually proves its consistency, naturally formalized consistency, and T is consistent. And what are we talking about here? Of course, we are talking about the formula formulated using this particular proof predicate here.
But we do not require T to be sound in the sense of item 5.
In fact, it will be sound.
Uh-huh.
Well, its consistency is in fact equivalent to its soundness because of the simplicity of axioms, let's say. But in fact, but I'm not claiming that the axiom. So what I'm claiming that the axiomatization of T0 is rather natural. So there's nothing. It is as natural a theory as any of those bounded arithmetic theories one considers. So there's nothing unnatural about T0. But there is something unnatural about T, namely T will be defined using fixed point lemma. So that new axiom will be defined using fixed point lemma, and in fact, okay, let's call it phi. So T will have the form T0 plus phi, where phi satisfies the equation that phi is equivalent to consistency of T0 plus phi. Okay, there is nothing surprising about such constructions. One can do it also for primitive recursive arithmetic instead of T0, or for piano arithmetic instead of T0.
Do you mean that this is the proof? That's it?
No, that's not yet a proof.
Otherwise, it's not clear why we need this.
But why?
Now let's
why it isn't a proof?
Because there is a second condition that our theory must be consistent. So if we do it for something usual, so to say, then if one rewrites this equation So phi is equivalent to consistency of itself.
So why phi not be just the false thing?
So negation of phi is equivalent to probability of negation of phi. And this violates Lev's theorem, so to say, or Gödel's second incompleteness theorem. Anyway, by Gödel's second incompleteness theorem, for normal theories, that phi would be simply inconsistent.
Yeah, so the simplest, looking at this formula, the simplest way to imagine such a phi is just to consider phi as a false formula. Then phi is false, and it's inconsistent, and you can prove this consistency, so everything is okay.
Moreover, Gödel has shown that in almost all reasonable cases, phi will simply be equivalent to falsity, if it satisfies this equation. So that has been noted many years ago. So people tried, of course, to formulate something like this. And they noted that, unfortunately, by this equation, we just get a falsity, and that's it. That's the only solution. But here, if we sort of severely restrict our language, so to say, in some sense, but do not restrict it in the other sense, we may achieve consistency. And let me prove now, the proof of consistency of that theory is fairly easy, so to say. It's not nothing.
But Lev, what sounds very strange, that we have no, in T0, we have no axioms which allow us to prove the usual properties of, say, sub or PRF. And also we add some strange formula which also doesn't prove any properties of these guys. How can we prove them?
Okay, so that's the continuation of your question at the end of last lecture. So let me tell you. So it does prove some properties of these functions, but in the following weak sense. Properties which are expressed in terms of concrete facts about concrete numerals.
And
so we don't need here any really universal statements or something like that.
And why do you think it proves something like that 2 plus 3 equals 5?
It will be obvious from the axioms of that theory. But basically...
which one?
I have not yet formulated what is T0.
So T0 is not any theory satisfying these items. It's a very specific theory.
In fact, it is a very specific theory. But, at the moment you can think about it as any things. But the point is that you asked a question about T0 proving certain property, which I don't need, if I had already all these properties 1 to 5. Okay.
Okay, let's see what happens, because now it's a kind of miracle theory.
Let's do it like this. Let's approximate this proof of this Wheeler's theorem, so to say, by stage. So let me first general outline, and then I will elaborate something.
I'm sorry. Before starting to prove the theorem, we need to understand its statement.
Okay.
So is there any quantifier over T sub 0?
No. T sub 0 is
something fixed. Think about T sub 0 as something fixed.
So the theorem
was
not
yet not formulated, definitely.
Okay.
And probably will not formulate it completely even later. But still, that's just a kind of...
Yes, absolutely. Yeah. But, well, I have no chance of proving it in full details.
Okay. It's formulating it.
Yeah. But of course it's easier to prove than to formulate.
Yeah, of course. Not quite. Well, let's do it like I suggest to you the following game. Let's do it like this. Think about T0 as something arbitrary satisfying these conditions.
Okay.
And find a place in my argument when you need something extra.
Okay. And just tell it.
And tell it to me, and then we will either add another condition, or I will tell you, okay. What I did was drastically false. Anyway, good. Okay, in fact, the proof is actually shorter than... okay, I erased some of these lines here. Okay, so the proof begins like this, by the following remark. So why did we need all these non-gross? So the essence is this non-gross restriction. So let us define the following. So height of a formula phi in the language of our theory is maximal constant occurring in phi. So what are the constants occurring in phi? Now first of all, these are these constants denoting fixed natural numbers. And secondly, these are the constants C coming from these non-growth conditions. So we count them as well. So height of phi must be sort of the supreme of all these constants. Since, well, phi is built from finitely many function symbols, so we have a well-defined concept. And then we have the following lemma, or I would say observation. So if we have a formula phi which is true in the standard model, and phi is phi of n, then phi is true in the following model Mn, where n is of course just the initial segment of natural numbers up to n, where n is the height of phi. This is precisely what we get from these non-growth conditions. Why does it hold? Well, basically, n is chosen in such a way that Mn will be closed under all the functions occurring in phi. And all the quantifiers, let's say, suppose first that phi is bounded. If phi is
Yes, wait a minute. Please separate the conditions of the lemma and the statement somehow.
Yeah.
Okay, then. Before then we have conditions. Good.
So first look at bounded formulas, then we claim that for bounded formulas we have actually even only if statements. So bounded formulas are absolutes. So this is sort of trivially verified by induction on the build-up of the formula phi. So the key point is that Mn is closed under the functions. If it is closed under the functions and quantifiers are bounded, then the meaning of the bounded quantifiers in this finite piece is the same as in the big model. So that thing holds.